Hello, everyone, and welcome to the seventh topic in the SS3 first term physics curriculum. Now, to those of you who have been part of our videos so far, you know just how we do it. I will ensure that we explain every necessary detail that is contained in the curriculum from week 1 to the end of the week for each of the terms. And this is the topic for week 7. The topic itself says magnet and magnetic field. Now, this is not something that is new to us. We've been introduced before now to the different types of force fields that we have. And we have such as the magnetic field, the gravitational field, and of course, we also have electromagnetic field. Now, when it comes to magnet and magnetic field, these are the various aspects that we're going to cover in the topic. First off, we'll start with the concept of magnetic field, where we'll look at what a magnetic field means, where we'll look at magnetic line of force, and then we'll describe each of those phenomena. Now, we go to patterns of a magnetic field. That is, we look at a magnet and the pattern of the magnetic field around a magnet, the pattern of magnetic field around two magnets, whether it is of like poles or unlike poles facing each other. After which we'll then look at the magnetic field around a straight current carrying conductor, because there is a relationship between magnetic field and electric field, just as we have relation between magnets and electrons. Okay, so when you have a conductor carrying current, what is the magnetic field around that current carrying conductor is what we'll be looking at this point. There's a simple law we're going to look at that point that will help us to understand the pattern of the magnetic field around a current carrying conductor depending on the direction of the flow of the current. Now, once we're done with that, we then go to magnetic field around a solenoid. We start by looking at what a solenoid is and what is the magnetic field around it. We'll draw the field pattern as well at that juncture. After which we then look at magnetic and non-magnetic substances. Now, these are different substances. They have their meaning. We look at what is a magnetic substance with examples, and we look at non-magnetic substances as well with examples. Then we look at how do we make magnets. That is the various methods of making magnets. Then we also look at, can a magnet actually lose its magnetism? Now, that phenomena is called the demagnetization of a magnet. So we look at the process involved to demagnetize a magnet. After that, we then look at magnetic properties of iron and steel. And then we look at what is known as magnetic screening or magnetic shielding. Now, by the time we have done all of these, we should have covered most of the things that involves magnet and magnetic field. Then we now look at relations between magnetic field and electric field, building what we know as the electromagnetic field. So we look at what electromagnets are and the applications of electromagnetic field. I've mentioned this before, that whenever you see EM field, the EM stands for electromagnetic. Okay, so we look at the applications of electromagnetic field in devices such as the bells and the likes. Then we look at Earth's magnetic field in detail. Earth has its own magnetic field. What's the pattern? We look at angle of inclination. We look at angle of dip. Those two different phenomena there are some of those things that are usually asked in exams, especially the JAMB exams. You could be asked to find the angle of inclination and the angle of dip. So we'll be showing you how to solve problems like that. And then we end up on magnetic force on a charge moving in a magnetic field. That is, whenever there is a charge moving in a magnetic field, there appears to be a force acting on that charge. So we look at how to calculate that charge, which will lead us to problems on magnets and the magnetic field. Now, this is what we are going to be looking at in this topic. It looks quite like a long ride, but trust me, just like we do right here, we ensure that every of the steps is explained to detail such that you can easily understand. And this is something that you don't want to enjoy all by yourself. So please be a good person, share this video. Let others enjoy what you are getting right here on Oya Learn Your Flawless School 2. Please click the share button and make sure that you are subscribed to the channel, and don't forget to click the notification bell icon so that you don't miss any of the amazing content that we put out right here on our channel. And be rest assured, if you have any challenge at all on any of the things that we are doing right here, you can always put a question across to us. All you need to do is put it in the comment section, and we promise to attend to all of your comments. So now that all that is said, let us dive into the world of magnets and magnetic field. To understand the concept of a magnetic field, think of it like this. If you do have a magnet and then you place it within, for example, close to a table, and then there are some materials around, magnets, metals, and the like, you see that it begins to pull these metals towards itself. And sometimes when you place other magnets, it pulls it when they are in some kind of orientation, and then repels in another type of orientation. That is the arrangement of the poles of the magnet. Now, let's assume you now pick just one thing here, either a magnet or a metal object. You find that when you place it at some distance, there is no pull on the metal from the magnet. But as it comes closer, it gets to a certain distance where it just drags the magnet or the metal towards itself. So that tells you that it has a limit or a range to which it can influence the movement of another magnet or another metal. Okay, now what this helps us to understand is that every magnet has a field around it, and any magnetic material placed within that field will experience the influence of that magnet. That is, they are forced into motion by the result of the magnetic field that is around that magnet. And that simple concept is what explains what we know as magnetic field. So if we are to define that, we'll say a magnetic field is a region or space around a magnet where the magnetic influence of that magnet can be felt or experienced by other magnets or magnetic substances. Let's put that down. A magnetic field is a region or space around a magnet where its magnetic force or influence can be experienced. And this is how we define a magnetic field. But it doesn't end there. You see, when we talk about the area around a magnet, there are some specific patterns through which magnets influence other materials to move. Now, this field itself is not visible, but we can map it out by using the compass needle. Now, when you place a compass over a magnetic field, you see that the needle will first spin around, and after a while, it balances in one specific direction, which proves that a magnetic field is a vector field, which means it has both magnitude and direction. So in order to map this out, there's something called the magnetic line of force, which is also important that we study. Now let's define what a magnetic line of force means. Magnetic line of force is an imaginary line where a free north pole will follow when placed in the magnetic field. Okay, what this means is that whenever you place an end pole, that is north pole of a magnet within a field, there's a direction or a path that it follows. Now that path there describes the magnetic line of force. Now it is imaginary in the sense that it is not something that actually exists, but it is what we use to describe magnetic phenomena. Okay, so it's something that we create in a way to explain how magnets behave in a magnetic field. So these two concepts help us to understand the full concept of a magnetic field. First, understanding that the field itself is an area, a space or region where the magnetic force from a magnet can be experienced, and that whenever you place a free north pole in a particular field, there exists a particular path that is going to follow, and that path is known as the magnetic line of force. To study the patterns of a magnetic field, you can use magnets and what is known as the ion filings. Now, when you place a magnet behind a petri dish and then sprinkle ion filings and then tap it in such a way, you see that they begin to form a specific pattern showing how the magnetic field around that magnet looks like. Now, based on the fundamental law of magnetism, we can begin to find different type of patterns around, for example, a singular bar magnet. Then there is a different pattern that you see when you have two magnets with the opposite pole facing each other. And then a different pattern is set whenever you have two magnets with like poles facing each other. So let us look at these three different phenomena and look at what the pattern of the magnetic field looks like. So we'll be starting first with when you have a singular bar magnet. Field pattern around a singular bar magnet. Okay, now what a bar magnet looks like is something like this, just like the name suggests, is a simple bar. Okay, and it has two poles, the north pole and the south pole. So let's divide that with a line like this. Now, by the time you tap around the petri dish, the pattern that will form with the ion filings will look something like this. Now, because it is a vector property, it has direction. Now, the direction is that it always moves from north to south. So the direction moves out from the north and comes in to the south. Okay, so it means here too you're going to have something like this. Okay, all of this showing the direction of the field. So it means that any free end pole that you put within this field will follow these lines towards the south. The north pole will always go this way to the south. And if you place a south pole within this north will have to move to meet that particular south along these path lines. Okay, now there's something you can learn from these path lines, is that whenever you have a large number of lines representing the pattern around a magnet to show the magnetic field, it shows that that particular magnet has strong magnetism. Now, in the case of a weak magnet, the field lines is going to be fewer. So what I'm saying here is that the more the field lines, the stronger the magnet itself, and the lesser the field lines, the weaker the magnet is. And don't forget that in this field pattern, the direction, because it's a vector, is from north to south. And this is the field pattern around a singular magnet. Now let's see what happens when you place two magnets such that the unlike poles, that is opposite poles, are facing each other. In this case, where we have two magnets and the pole facing each other are similar, let's take north to north, for example. What will happen here is repulsion occurs. And of course, the direction is always north out, north out, north out. Okay? So what you see here, instead of them coming together, they are pulling apart from each other, showing what? Repulsion between the like poles of two magnets. Now the same thing happens when you have the south to south. The only difference is the direction of the arrow. So what that will look like is something like this. Let's do it here. South to south. So okay, so the direction of the arrow is inward as a result of the north pole on the other side. Okay, so this also shows that they are trying to pull apart from each other, meaning that they are sliding towards the north pole on the opposite side of this bar magnet. So in this case, and in this case, we have repulsion between like poles of two magnets, and the lines there shows us the field pattern for the magnetic field between these two magnets. And as it indicates, based on the direction, we can see that there is a repulsion there. Don't forget, if you do have any question on this, you can always drop it in the comment section and we attend to all of your comments. Now let us consider the magnetic field around a straight conductor carrying current. Now, whenever you have a conductor and current is flowing through this conductor, there appears to be a magnetic field around it. Now, how this can be done is by testing it with your right hand. Now, let's assume that the conductor now is this pen in my hand. Now, when you grip it in such a way like this, you see the way I'm holding it, right? You see that my thumb is pointing in a particular direction and the other fingers are wrapped around the conductor, which is the pen in this case. Now, in this situation, when you wrap it like this, such that your thumb is pointing in the direction that the current is flowing. Okay? Like this case now, you see, the direction of this current here is where? To the right. So now I'm holding the pen the same orientation as this conductor here, and my thumb, as you can see, points in the same direction as the direction of the current. Now, the direction of the other fingers curled around the conductor shows the direction of the magnetic field. So meaning that a magnetic field is around it like this. Okay? And the direction of that magnetic field is what? Just like in the case of the pen, as you can see here, okay? It will be flowing like this around it. So that is, you are having it coming this way, coming this way, around it. It goes around it. So when you have the conductor like this, the magnetic field around it is going like this, in this direction, because that's the direction that my fingers are curled around the conductor. Okay? Let's put that down in a statement. When the right hand holds a straight conductor. The direction of the thumb can be made to represent the direction of current through the conductor. Now, if this is done, then the direction of the other fingers curled around the conductor shows the direction of the magnetic field. Around the straight current carrying conductor. Now, this statement goes on to explain how magnetic field and electric field relate with each other. So once again, so you get it. If you have a straight current carrying conductor and you grip it with your right hand in such a way that the direction of the thumb shows the direction of the current through the conductor, then the direction of the other fingers that are curled round the conductor shows the direction of the magnetic field around it. So every time you draw a current carrying conductor and you have the direction of the electric current through it, you can use the right hand grip to show the direction of the magnetic field around it. Let us now look at the magnetic field around a solenoid. The first thing we need to look at here is to know what a solenoid is. So it is a cylindrical coil of wire. Now, it is wound in such a way that the coils are closely packed together. So what you're having is something that looks a bit like this, but let's first write down the description of a solenoid. A solenoid is a cylindrical coil of wire wound closely together. Now, you see the ends of the coil. When you connect it to an electromotive force source, that is a EMF source, that is a cell or a battery, current will flow through the coil and that will create a magnetic field around the solenoid. And the pattern of the magnetic field is going to look a bit like this. So let's take this as a cylinder representing the solenoid. Remember that around the solenoid we're going to have a coil, right? So, okay. Okay. This line showing the coil. And then we go on to apply an EMF source at this end of the solenoid. Now, this is what will happen. You begin to see that once current is flowing, this will be the direction of the current, of course. This is direction of current from the positive terminal of the cell, and it continues to go around the coil like that, like that, like that, and comes back to the negative terminal, and the cycle continues like that. And as a result of this, there will be a magnetic field in and outside the coil, and that magnetic field will look like this. So let's take now the direction of this particular field will be, for this one that is down here, will be counterclockwise. That is, you have the magnetic field going in this direction, and this one is going to be clockwise. Okay, what you have to take note of is the direction of the current. If this current is going like this in the clockwise direction, the one close to this electric field here will be counterclockwise as it relates with the field here, and this would be clockwise as also relates with the field. So these particular lines here is showing the pattern of the magnetic field in and outside the solenoid, while these lines are showing the direction of the flow of electric current through the coil of the solenoid. And this is how we represent the magnetic field pattern around a solenoid. Let us now look at the magnetic field around a solenoid. But firstly, let's describe a solenoid. A solenoid is a long cylindrical coil of wire whose turns are closely wound together. Okay, now when you have the solenoid and you pass electric current through the coils of the solenoid, there's going to be a magnetic field in and outside the cylindrical coils of the solenoid, and it follows the pattern shown here. So let's take this to represent the cylinder around which we have the coils of our solenoid. So let the coil start here such that it comes, okay, I'm trying to draw them slightly apart so that it doesn't look too clumsy, but please take note that these coils are tightly packed in real applications. Okay, and then we're going to connect this to a EMF source, that is a cell like this. Now once you make this connection, there will be a flow of current through the coils and it follows this pattern. You can see the direction of electric current through the coils of the solenoid. Now, as the current begins to flow, remember that when you have a current carrying conductor, there is always a magnetic field around it. We have already looked at what happens when you have a straight current carrying conductor, and we represented that with the right hand grip. But in this case, what you're going to have is a magnetic field in and out of this, like this. The same thing here. Now, what will be the direction of the magnetic field? You see the ones close to the cell like this, we follow the same direction as what we have here. Okay? While this one will be the reverse direction of the current. So you have the current, the magnetic field following this direction counterclockwise, like this. So At the top half here, we have a magnetic field in this direction. At the bottom half here, we have a magnetic field in this direction, while the current is flowing from the positive terminal like this through the coil, like that, and then out back like this to the negative terminal of the cell. And this is how we represent the magnetic field around a solenoid. Now that we have learned about magnetic field and we've seen various magnetic field around different magnets, when we have bar magnets, when we have magnets with opposite poles facing each other, like poles facing each other, we've seen magnetic field around current carrying conductor, magnetic field around a solenoid. Let's now look at what magnetic and non-magnetic substances are. Now, to define magnetic substances, these are materials that can be influenced by a magnetic field, meaning that if you place them in a magnetic field, they are either attracted or repelled by the field. So they experience magnetic force. And then the non-magnetic substances are those ones that are not affected by magnetic field. So when you place them in a magnetic field, they do not get affected by the field, they remain inert. They don't react to the magnetic field. And there are examples of them. But first, let's write down the definitions. A magnetic substance is any material that is affected or reacts when placed in a magnetic field. And you know what this means? That is, whenever you put it in a magnetic field, it's either it is attracted by the magnet or repelled by the magnet. So there is always a reaction to the magnetic field. And examples include iron. Iron is a magnetic substance. Steel is a magnetic substance. Cobalt is a magnetic substance. Nickel is a magnetic substance. Manganese is also a magnetic substance. You see, these 5 materials I've mentioned, whenever you find any material made up of either one or a combination of these materials, when you place it in a magnetic field, they are affected by the magnetic field. They are attracted by magnets. And they themselves can be magnetized as a result of that. Okay, these are what we know as magnetic substances. Now, on the other hand, non-magnetic substances are materials that are not affected when placed in a magnetic Now, there's a common misconception when talking about magnetic and non-magnetic substances. Many believe that magnetic substances involve metals, just metals. Okay, but when you consider the materials of each of these, the properties rather of all these materials that are magnetic substances, they vary. And the same thing applies to non-magnetic substances. Many would think that there would be materials that are non-metals, but there are even metals that are non-magnetic substances. So let's list some of those in our examples. So examples of non-magnetic substances, examples include aluminium, zinc, wood, cotton, glass, etc. All of these are non-magnetic substances. And this is because whenever you place them in a magnetic field, they are inert. They do not react to the magnetic field in any way. And this is how we describe magnetic and non-magnetic substances. Please put in the comment section other examples of non-magnetic substances that you know. Now that we understand what magnetic substances are, let us now look at the various types of magnets that we have. Now, there are several ways that types of magnets may be explained to you, but to keep it simple such that it is easily understandable, I'm going to group them into two specific categories. Now, the first category we're going to be looking at is known as the natural versus man-made magnets. Okay, now this tells us that when we're looking at types of magnets, we could group them as the ones that exist naturally, that is the ones found in nature, and the ones that are made by man. And you see, in the case of natural magnets, it has an interesting backstory. We hear of story of a particular shepherd known as Magnus, who lives in a city known as Magnesia in ancient Greece. Now, as customary for shepherds, they often go around holding staff. Now, to make their staff strong, because they have to break rocks as they move and things like that, they often attach metals to the base of their staff. So Magnus, on one of those days while he was going with his flocks, I was touching the ground with his staff and discovered that I got to a particular point and the staff got stuck to a certain rock. And he tried so hard before he could pull it away, and then tried again, and he saw that it was always attracted to that particular piece of rock. And that is how magnets were first found in nature. Now, that particular rock is known as a lodestone or magnetite, named after the city of Magnesia, of course, which is why magnets take the name magnet after Magnesia. Now, this is a naturally occurring magnet. Naturally occurring magnet. Now, there are some things you should know about this. You see, the lodestone comes in a very irregular shape, so it does not have a specific shape. The magnetic property of lodestone is very weak, so it's not very strong like that. Yes, it attracts metals and other things, but it's not very strong, and it does not have specific shape. I've mentioned that already, that it comes in an irregular shape. Okay, so that's the case of natural magnets. Now, for the man-made magnets, these are magnets that are made from magnetic substances through different means. Now, mind you, there are different ways you can create magnets, okay? But once it is created by man from magnetic substances such as iron, steel, and the likes, what you are creating there is known as an artificial or man-made magnet, okay? And in the case of artificial magnets, they can be made in any shape you want, and they can take shapes. And some of those common shapes are, you can either have it in bar form, you can have it in horseshoe, that is the horseshoe magnet, you can have it in disc shape, you can have it in circular shape, curved shape, different types of shapes of the artificial magnet. You create it to make the type of shape that you want it to have. And you can always alter the magnetic ability of your artificial magnet. But in the case of a lodestone, whatever magnetic ability it has is inherent. It's there like that. You cannot alter it. You can't change it. It remains like that. But for the artificial magnet, you can always create it to be either strong magnet or weak magnet, depending on what purpose you want that magnet to serve. And that helps us to understand this category of magnets, that is the natural against the man-made magnets. Now, for the second category we're going to be looking at what is known as the temporary magnet versus permanent magnet. Now, the temporary and permanent magnet are both artificial magnets. But here's the thing. Temporary magnets, they are made from soft iron. And they lose magnetic ability easily. Now, on the other hand, the permanent magnet is made from steel and it cannot be easily demagnetized. And these are the various types of magnets. So to recap, remember that we have natural and man-made magnets, where example of the natural magnet is the lodestone known as magnetite. Okay? And that's where the name comes from, because it was found in a city called Magnesia in ancient Greece. So that's why we named them magnets. And then we have the artificial magnets, the ones that is made by man, that can take any shape, and you can always create it to have certain strength of magnetism. And then the second category of magnets is the temporary and permanent magnet, where the temporary magnet is made from soft iron and it can easily lose its magnetic ability. That is, you can easily demagnetize it. And then we have the permanent magnet that is made from steel and cannot be easily demagnetized. Don't forget, if you do have any questions on these various types of magnets, you can always drop it in the comment section and we attend to all of your comments. So now that we know that there are artificial magnets, let us look at the various methods that magnets can be produced. Now, there are quite a number of methods by which you can make magnets, but there are four prominent ones which we're going to discuss in this video. Now, those four methods are as follows. We have the electrical method, of making magnets. We have the one-touch contact method. We have the double touch contact method. And then that's number 3. And then for number 4, we have the induction method. Now, in the case of the electrical method, it is actually the quickest way of making a magnet. This is why this is the method that is employed industrially for making magnets. Now, what happens in this method is, whatever material that you want to magnetize will be placed in the cylindrical core of a solenoid. And then by the time you allow current to flow through the solenoid, after a few seconds, that material gains magnetic properties. That is, it becomes magnetized. So like for example, if you take a soft iron and then you put it into a solenoid and pass electric current through it, what you'll be producing after a few seconds of allowing current to run through it is a temporary magnet. But when you put a steel material in the cylindrical core of a solenoid and allow current to flow, you'll be producing a strong magnet. Now, aside that, the amount of time for which you allow current to flow can also determine how strong the magnetic ability of the material would be. So whether it's a temporary magnet or a permanent magnet that you are making by electrical method, The longer the time, the stronger the magnetic ability of those magnets. Now, in the case of the one-touch contact method, in this particular method, you have a material and then you begin to stroke it with a magnet. Now, you're going to be sliding the magnet across it like this. Now, as you continue to slide it, it takes a very long process. But after a while, this material here becomes magnetized. By the time you stroke it continuously like this for a very long time, it becomes magnetized. Now, it's a very less efficient method of making magnet because it takes a very long time, and you have to always test to see when the material becomes magnetized, and the strength of the magnet is not always very strong. And the same thing applies for the double stroking method, except that in this case, the material will be stroked with two magnets. So you have one magnet on one side and another magnet on the other side, and then you stroke. As you continue to stroke them like that, after a long period of time, this material also becomes magnetized. So like in the case of the single stroking or the one-touch contact method, it is also a long process of making magnets. And then the final method we're going to talk about here is the induction method. And this one is something that you've probably seen. Now, whenever you put a metallic material on a magnet for a very long time, you often see that that material itself becomes magnetic. Take, for example, if you store nails in the house by keeping them on a magnet, after a while, when you pick up one of those nails and you put it close to another nail, it sort of attracts the nails and picks it up easily, right? That method of creating magnets is known as the induction method, where a magnetic substance is placed on a magnet for a long time, and as it cools and heats up on the magnet, after a while, that material also becomes magnetic. Okay, so it's one of those ways you can also create a magnet. Now, when you look at all the various methods here discussed for making a magnet, you see that the one that is quick and the one that is reliable is the electrical method, which is why till date the method used to create magnet is mostly the electrical method. Now, it does not disapprove these other three methods. They also provide magnet, they produce magnets, but it takes a long process. So if you want to really produce a magnet and see it have magnetic properties, the fastest way to do it is by electrical method. However, these three other methods will also produce you magnets. Okay, there are other methods you can take a study and look at how you can also produce magnets. I believe you can also produce magnets by hammering them around Earth's magnetic field. This is why whenever you hammer strong iron, sometimes after a while they tend to have magnetic property as well. So many other methods like that to make magnets, but these four are the ones that you really need to put to mind and remember all the time, especially when it comes to exams. These ones are required at the senior secondary level, that every student know how to produce magnets by electrical method, by one-touch contact method, by double-touch contact method, and by the induction method. If you do have any question, please put them in the comment section. We attend to all of your comments. Now that we know how to produce magnets, it's also important that we study demagnetization. Now, in case you're asking what does demagnetization means, it is a process whereby a magnet is made to lose its magnetism. Let's note that. Demagnetization is the process where a magnet is made to lose its magnetism. So that is, a magnet, when put through the process of demagnetization, will lose its magnetism and will no longer be a magnet. Now, there are three main methods by which you can make a magnet to lose its magnetism, and those three methods are: 1, by electrical method, electrical method, 2, mechanical method, and thirdly, heating. Now, when it comes to the electrical method, we know that when you place a magnet in a solenoid and allow current to flow for a short time, it gains magnetism. That is, whether it's an iron, soft iron, or a steel, when it is placed in a solenoid and then you allow current to flow, it becomes magnetized. Now, all you need to do is reverse the direction and place the solenoid to face the east-west direction and allow alternating current to flow through the solenoid. Now, by the time you withdraw the magnet slowly from the solenoid and take it far away from the solenoid, it will be found that that magnet is no longer magnetized. That is, it has lost its magnetism and is no longer a magnet. Another way is to hammer a magnet when it is facing the east-west direction. Remember that when you hit a metal, that is a iron or steel bar, when it is facing the north-south direction, it can gain magnetism. So by the time you reverse this and make it face the east-west direction and hammer it down, it will also lose its magnetism. And then finally, whenever you place a magnet into you pass it through strong heat, that is, you heat it up, you raise the temperature of the magnet, it can be found to lose its magnetism. This is why most times when you place magnets under hot sun, when you place it in a situation where the temperature is very high and then you try those magnets afterwards, you find them to become weaker and weaker until they no longer have their magnetic property. So either of these three methods will make a magnet lose its magnetism. And the process through which it loses the magnetism is known as demagnetization. Whenever we use electronic equipment around us and some other kinds of machines, because of the material makeup of this machine, they tend to interact with magnetic fields around them. Now, this magnetic field can make the machines to function in ways that it ought not to, thereby giving you a result that you do not want. So when this happens, you want to ensure that there is no such interaction because you want that machine or gadget to provide you the specific result that you want from it. Now, one of the ways you can protect this kind of gadgets or machines from this external magnetic interference is a process known as magnetic screening or shielding. Now, this is how we define magnetic screening or shielding. This is a method of protecting electronic equipment from external magnetic field. Now, the way this happens is we already understand how magnetic fields interact, and we know that they easily permeate soft iron cores. So what you need to do is get an iron core like this, okay? And then place whatever equipment you are using inside the iron core, that is within the iron core like this. Now, whenever there is any magnetic field around, so let's build an external magnetic field, for example. Let's say we have a north pole here and then a south pole here. What will happen is that this will create magnetic field. Of course, every magnet has a magnetic field around them, and the direction of the field is from north to south. Now, normally, this would go straight to the south if we didn't have this soft iron core here. Remember, this is a soft iron. Okay? And this is the north pole and the south pole of the magnet. Now, this soft iron allows magnetic field to run through them. So as a result, the field line of this magnetic field will follow this path. Now, this would be the path that the magnetic field will follow. Don't forget the line. and direction has to be from north to south. And as you see here, you see that this field conveniently avoids this center area of our soft ion. So whatsoever you place within this space here is the shielded space. Shielded space. Anything placed within this space here is protected completely from any external magnetic field. So you see, this is the setup known as magnetic screening or shielding. And we use this quite a lot. Like in the medical field, it is used in MRI machines. In communication field, it is used for transmission cables, such as the coaxial cables and the likes. They are always wrapped with soft iron so that they do not interact with magnetic field from the external sources like that. So all of these has a lot of applications. Even in the cathode ray tube, it is also used to protect it from external magnetic field. Don't forget, this is a method of protecting equipment from external magnetic field, and the name of this method is called magnetic screening or shielding. Another important aspect in our study of magnets and the magnetic field is the applications of electromagnets. Now, you'll be surprised there are a plethora of devices around us that uses electromagnets. Okay, but before we begin to look at these applications, the first thing we need to ask ourselves is, what are electromagnets? Now, you see, to define this simply, electromagnets are temporary magnets. Now, they are made by passing current through a coil of wire. Now, that coil of wire we're talking about is what we call a solenoid, right? Remember that in a solenoid, the coil are tightly wounded together. Okay, so we have a coil of wire that are very close to each other, while a soft iron core is embedded within the coil. Okay, so if you're asked what an electromagnet is, this is what you say. An electromagnet is a temporary magnet made by passing electric current through a coil of wire solenoid containing a soft iron core. Now, when you have this temporary magnets, it has a plethora of applications. Some of the applications are as follows. It is applied in production of intense magnetic field, such as the ones that are required in generators and electric motors. Now, when you study the principle of operation of generators and electric motors, you see that there is always constant spinning. There is that mechanical action that has to continue, and it is always done with the aid of magnets. So the magnets used in this case are electromagnets, temporary magnets produced by passing electric current through a solenoid containing a soft iron core. So that's one of the applications of electromagnets. We also find another application in the case for lifting and transporting heavy pieces of iron and steel. Now, when you go to industries where they produce large metal bodies, for lifting these metal bodies, one way you can do that is to use cranes that are fitted with electromagnets. So once they come in contact with it, they pick up these metal objects, and then you can place them in storage devices or in storage trucks where they can then be transported from one location to another without any hassle whatsoever. Another place where it is applied is whenever you need to separate ions from mixtures or containing non-magnetic substances. Like take for example, when you go to scrap yards, when you go to metal producing companies, what they do is they get a lot of scrap materials containing metals. Now these are the metals that they will have to heat up to molten stage and then use it to produce iron rods amongst other kind of metal objects. Steel companies do this a lot. Now when they bring in all the scrap metals, oftentimes they are always mixed with so many other non-magnetic substances. And to produce good steel, you have to make sure that the quality of the metal you are heating up is good enough. You don't want to heat it up with other things that can affect the production process. So one way they separate it, because they are dealing with a large bulk of metal load here, so many scrap metals, and you want to separate them from these non-magnetic substances. So one way to do that is to use these electromagnets to separate them. Remember that they will attract metals, while non-magnetic substances will not be attracted by the temporary magnets, that is the electromagnets used in this case. So it is used in steel companies, in scrap yards and the likes to separate metals, iron especially, from non-magnetic substances. Other applications include, in the case of electric bells, now in the electric bell itself, it is the electromagnet that actually pulls the hammer that hits the bell. So whenever you switch on an electric bell, know that it's an electromagnet that hits the hammer that rings the bell itself. It is also used in production of telephones, loudspeakers, headphones to vibrate the diaphragm that produces the sound that we hear from the telephone, the loudspeaker, and our headphones. It is also used in data storage for production of data storage devices, from your hard drives to even chips that are used in credit cards and the likes. They contain electromagnets in nano forms, of course. And then we also use them in the medical field in the machine known as the MRI scanner. It uses a magnetic field produced by electromagnets. Now, these are just some of the applications of electromagnets. Like I mentioned, there are a plethora of its application. It's used a lot around us. From these ones that we mentioned, you're beginning to identify some of these applications that you use. Like for example, when you see electric bells now, you know that it applies electromagnets to pull the hammer that rings the bell. When you use your telephone, your loudspeakers, your headphones, you now know that they also apply electromagnets to vibrate the diaphragm that produces the sound that we listen to with this particular device, the headphones, the loudspeaker, and the telephone. And you can also see in the case of generators and electric motors, they also use electromagnets. These are just 7 out of all the applications that you can think of. So please drop in the comment section other applications that you know of electromagnets. Let's discuss, how do we use electromagnets around us? To understand angle of declination, let's consider a compass. Now, when you use a compass, you will observe that the compass needle itself does not always point to the true north or the true south. Okay, now this is because there's usually a tilt. Now remember when we drew a diagram to show the earth earlier, we did something there where we mentioned that the magnetic north pole is tilted a bit. So magnetic north pole, and then this is geographical north pole. Then here we have the geographical south pole and the magnetic south pole here, showing that the magnetic field of the earth is slightly tilted. If it's represented by a bar magnet, we'll have something like this. Okay, now when you look at this magnetic north pole and the magnetic south pole, you see that they are slightly tilted from each other, and the compass needle you are holding is going to be moved not by the geographical north or geographical south pole, but rather by the magnetic north and magnetic south pole. So when you use your compass needle to find direction, okay, there's usually an angle, a tilt between the true north and the magnetic north of that your compass. Okay, the same way there's always a difference between the true west from the magnetic west of what your compass is showing you. Now, this difference in the angle is what is known as angle of declination. So if we're going to define angle of declination, we'll say angle of declination is the difference between the magnetic and geographical meridians of a location. So for example, if your compass needle is pointing you to the north and that north is 5 degrees east of the true north, that means that your angle of declination in that situation is what? 5 degrees. Whether it's to the east or to the west. In this description, I said it is 5 degrees east of the true north. So the angle of declination is 5 degrees east in that case. So basically what I'm saying is this. If you have a geographical meridian in this direction, geographical meridian, and then this is pointing to your magnetic meridian. Okay? This angle between them here, theta, is known as your angle of declination. Now let us look at what angle of dip means. To understand angle of dip, we have to still recall the Earth's magnetic and geographical points. Okay, remember that when you have the Earth, if this circle now represents the Earth, we have the magnetic north pole here, the geographical north pole here, we have the geographical south pole here, and the magnetic south pole here. Now there is an imaginary line that runs across the Earth, divided into 2 equal halves, known as the equator. Okay, just as we have an imaginary great line here too, known as the Greenwich meridian. Okay, remember this is Greenwich meridian and this is equator. Now, whenever you use a compass needle on the surface of the Earth, there are some things you're going to observe. Okay? Take, for example, a person who is along the equator. Okay? Along the equator, the compass needle stays nearly horizontal. Okay, so that is when you stand along the equator, your magnetic needle is going to be almost flat. Okay, so at that point, that's what you experience when you use a magnetic needle or your magnetic compass. Okay, now, but by the time you get to the pole, at Earth's pole, the compass needle points slightly downwards. Okay, so that is when I'm here, you begin to see it slanting, sort of like this, along this line like this. That's how it begins to bend when you are at the poles, whether at the South Pole or at the North Pole of the Earth. Now, this helps us to understand the angle of dip. So to define it, we say angle of dip is the angle between the direction of compass at a location to the horizontal. Now, what this means is this. If you are at the poles of the earth, your angle of dip is nearly 90 degrees. At earth's pole, angle of dip is approximately 90 degrees. While at the equator, angle of dip is approximately 0 degrees. Since we are looking at the angle between the direction that your compass needle will face to the horizontal now being the equator. So we always measure it at the horizontal level at the equator. So if you are any other point here, you're going to measure the angle that the needle is pointing to compared with the horizontal line at the equator. And that difference between the angle is what gives us what we know as the angle of dip. And it's a common question you will always find, especially in the JAMB exams. And most times they tell you a certain person is, for example, at the equator. What will be his angle of dip? They did not mention an angle to you, so you begin to rack your head and think, oh, what will be the angle of dip at this location? Don't forget, when you are at the equator, the compass needle is almost horizontal. But when you are at the poles, it is almost vertical. So that is why at the poles you get 90 degrees angle of dip, while at the equator you get 0 degrees angle of dip. And then it varies as you move between the equator and the pole, equator and pole vis-a-vis. This question from the JAMB of 2019, for example, it says that the Earth's magnetic equator passes through Jos in Nigeria. Now, at Jos, which of these statements will be true? Okay, so what we know here is this. When you are at the magnetic equator, a compass needle is going to be almost horizontal, that is approximately at horizontal. Okay, and one thing you can measure here is the angle of dip. Okay, and the statements we have here, we have in option A, angle of variation is 0. B says magnetic declination is 90. C says angle of dip is 0. And D says horizontal component of the Earth's field is 0. Now you see, as regards angle of variation and magnetic declination, they mean the same thing. So one cannot be 0 while the other is 90. So that tells you that these two are automatically wrong. Don't forget that when it comes to angle of variation or angle of declination, you are looking at the difference between the angle, the direction that your compass needle is pointing to the true direction it should be. That is, we are looking at true north and the magnetic north. The angle between the magnetic north and the true north is what we call the angle of declination. The same thing applies to the east, the west, and the south. Okay, so these two are knocked off. They are not correct. But when we look at angle of dip is supposed to be the angle from the horizontal to the direction that the compass needle is pointing. So since the compass needle is going to be horizontal at this point, so the angle between the direction of the compass needle and the horizontal is going to be 0, which means the angle of dip is 0. So the correct option here is C. Let's kill two birds with a stone using this question. Now this says to calculate the angle of dip for a place whose horizontal and vertical components of the Earth's magnetic field are equal. Now when it comes to finding the horizontal and vertical components of Earth's magnetic field, the same way we do when we're looking for horizontal and vertical components when dealing with vectors is just what you do at that point. You will always be given the angle of dip. Now for example, let's say the angle of dip at a location is say 60 degrees. The horizontal component of Earth's magnetic field at that point, B horizontal, would then be what? B cos theta, where theta is the angle of dip. Now sometimes angle of dip may be represented with this particular symbol, so please take note, it could be this or theta depending on the examiner, but this is what is most likely used to represent angle of dip. And then when it comes to vertical component, would be be sine theta if we are using theta in both cases. So now we have been given that the horizontal and vertical components are the same. So that is B of H equals B of V. So how can we then get the angle of D back? It's just simple. Look at the solution here. Let's take this to represent the horizontal component and this to represent the vertical component. Remember, angle of dip is supposed to be the angle between where the needle is pointing to the horizontal. Okay, we can always complete this by drawing a line like this. Okay, and we are trying to find this angle here. How do we find the angle? When we know this side and this side. Remember, we have this as B of vertical and this is B of horizontal. Okay, and we need this angle. Let's call this angle theta, for example. Okay, so what do we do to get theta here? We're going to say what? Apply trigonometric ratio known as the tangent. So tan theta is supposed to be what? Opposite BV over adjacent BH. So which means that theta becomes tan inverse of BV over BH. But BV equals BH according to the question, because we are told that horizontal and vertical components are equal. So if both of them are equal, it means theta equals tan inverse of 1. And this would give you what? 45 degrees. And this is the solution to the question. Whenever a charge Q finds itself in a magnetic field, it can experience magnetic force. Now, here's the thing. When the charge is stationary, it does not experience any effect from the magnetic field. But when the charge is moving, it experiences a magnetic force as it moves in the field. And this magnetic force depends on the following. It depends on the velocity of charge. The velocity is denoted V. It depends on magnetic flux. Now, another name for magnetic flux is the strength of a field, and that is denoted B. It is measured in Tesla. This is in meter per second. This is in Tesla. Okay? It also depends on the charge Q itself. Magnitude of charge Q, which is in coulombs. So let me put this Tesla in coulombs. Okay, and it also depends on the angle it passes the field, which is in theta, measured in degrees. Now, the relationship between the force and all of these that determines the force that the charge experiences is given by F equals BVQ sine theta. Now, there are a couple of things you must learn from this. Due to this angle, if charge is perpendicular to the field, then F is just BVQ. Now, the reason is this. When it is perpendicular to the magnetic field, theta becomes 90, right? And sin 90 will give you 1. 1 times BVQ remains what? BVQ. Now, if charge moves parallel to the field, it means theta is 0. Okay? That will mean that F equals 0 newtons. Okay? Because when you apply sine 0 is 0. 0 times BVQ will give you what? 0. So these are some of the ways that examiners tend to set the questions to test the knowledge of the students. If you understand how the angle affects the force on the charge, then you shouldn't have a problem when you are told that the charge is moving either parallel with the magnetic field or perpendicular with the magnetic field. Now, other cases are when you are given the angles to which it moves through the magnetic field, whether it's moving at 30 degrees, at 60 degrees, at 45 degrees, which is why it is important that you understand how to find sign of some special angles, some common angles such as 30, 45, 60 degrees, then 90 degrees and 0 degrees also being some of those common angles. But when it falls in between that, you just have to use your calculator or the mathematical table to solve your problem in those cases. Now, there's another situation entirely when dealing with forces on a charge moving in a magnetic field. Now, let's say that the charge is moving through a conductor. So when you have a conductor that is carrying current, in that case, you have to factor in the current to your calculation. Now, here are some things you need to take note of. Okay, let's do that here. Now, when you have a current, know that current is actually what? Charge Q over T. Okay? Another thing you should know is that V is velocity, right? Velocity is distance over time. So let's say the distance is length L, because it's going to move through a conductor, right, that has length L over time T. Now let's put this into the equation. What are we going to see? You will see that F now becomes what? B. Okay? And then instead of V now, we are having L over T times, instead of Q now, we can now write IT. And then you see T cancels T, which implies that F equals BIL. Sin theta remains, so we put it in the equation. So either of these equations will help you to solve the force on a charge moving in a magnetic field. Let's take a couple of examples so we see how we apply these equations to solve problems. Here is a question from the 2019 JAMB, and it says a straight wire 15 centimeter long carrying a current of 6 amperes in a uniform field of 0.40 teslas. What is the force on the wire when it is at a right angle to the field? Now, when it comes to calculating the force on a charge or on a current carrying conductor in a magnetic field, don't forget the two equations that help. It's either you are saying F equals BVQ sine theta, or you say F equals BIL sine theta. Now, since we are dealing with a current carrying conductor with current 6.0 amperes, it means we have to use the equation that has current in it. So F equals BIL sine theta will be our go-to equation. So here's the solution. F equals BIL sine theta. Now, before we apply this, here's something you should know. In JAMB exams, the calculator you are allowed to use is not a scientific calculator. So you have to be able to work with numbers like this. If you look at the kind of numbers we have here, 15 centimeters, you still have to bring this to the correct SI unit. 6, 0.4. These are numbers that when working with like this, without a strong calculator, you might have errors. So one way you can avoid your errors is to work with these numbers in fractions. If you are good with working with fractions, multiplication of fractions, division of fractions, addition of fractions, subtraction of fractions, you won't have issues solving JAMB exams. And remember that it's a time-sensitive exam, so it means that you have to do all of these as fast as possible. So if you are still not very good at working with fractions, improve on them. It's something that will help you solve problems like this in JAMB exams without error. Now, let me show you how you do something like this with fractions. Okay? Now, to solve this problem, we say the force equals what? B is the magnetic flux density, and we have that as 0.40 Tesla. Convert that to fraction. Don't bother about bringing it to its lowest possible fraction yet. Just convert it straight to a fraction as 4/10 straight away. Okay? Now we multiply that by the current. The current is given in whole number form, so we write that 6 times the length. The length is given in centimeter, which you have to bring to meter. and that is 15 divided by 100. Write it just that same way. Don't bother about bringing it immediately to the lowest possible fraction. Leave it like that. And then you multiply this by sine. Now the angle is what? Is at right angle to the field, so that means it is 90 degrees. Now what does this give us? Now let's break it down. Here now we can break it and say 2 goes here 2 times, 2 goes here 5 times, 5 goes here once, 5 goes here 3 times. So now we have 2 times 6 times 3 divided by 100 times sine 90 is what? 1. Now let's find the value of f. F being the first will now be what? 2 times 6 is 12. 12 times 3 is 36. Divided by 100. Times 1 still remains like this, and this is your answer in Newton. But when you look at the options we have, they are in decimal form, so convert this to decimal. So what we have here is what? 0.36 newtons. Making the correct option C. And that's the solution to the problem. Here's another question to try on solving problems involving magnetic force on a charge moving in a magnetic field. Now, in this question from the 2005 JAM, we're told that a proton moving with a speed of 1 times 10 to the power of 6 meters per second, that's about 1 million meters in a second, through a magnetic field of 1.0 Tesla, experiences a force of magnitude 8.0 times 10 to the power of negative 14 newtons. Now, we're asked to find the angle between the proton's velocity and the field, given that the proton has a charge of 1.6 times 10 to the power of minus 19 coulombs. Now, how do we solve this? Now, this is what we'll do. We're going to apply F equals BVQ sine theta. Now, F is given already as 8 times 10 to the power of negative 14 equals B, which is 1, times V, that's the velocity, 1 times 10 to the power of 6, and the charge, 1.6 times 10 to the power of minus 19. All of this sine theta. Now, this is where you need to get creative. All of this will still give you 1.6, okay? And then we can apply the law of indices for this part. Okay, but there's something you can do to this. Now, you can now say this is 8 times 10 to the power of negative 14 equals, now, instead of writing this, we now say 16, okay, times 10. Now, I'm using 16 here because I know I will still cross multiply and I have 8 here. It makes it easy to work with. And then we have 16, or let's just keep it at 1.6 first for now. I'll still turn it to 16 so that you get what I'm doing here. I don't want you to get lost with the mathematics involved at this point. So let me still take it step by step for you so that you can easily grasp what we are doing here. Okay, 1 times 1 times 1.6 remains 1.6. Now, law of indices will mean 6 minus 19, and that will give us minus 13. Okay? So, sine theta. Now, what does this mean? Let's take it from here. We now say sine theta itself now becomes what? 8 times 10 to the power of minus 14 divided by 1.6 times 10 to the power of minus 13. From here now, look at sine theta therefore becomes, and I say 8 times 10 to the power of negative 14 divided by, now move this a step further and say 16 times 10. It means you're going to subtract 1 from this and it becomes minus 14. Now look at what happens here. Times 10 minus 14 times 10 minus 14, 1. You see that now? So sine theta equals what? 8 divided by 16, that's 0.5. Now to find theta, we just say inverse sine of 0.5. And this would give us 30 degrees. So the correct option to go for of all the 4 options provided here is the one that says 30 degrees, which is option C. And that's the solution to the problem. To wrap up our study on magnets and magnetic field, let us take a look at some questions on magnet and magnetic field. Now, this particular one is from the 2004 JAMB, and it says to protect a material from the influence of an external magnetic field, the materials should be kept in, and then we have four options. A says a square steel ring, B says triangular zinc ring, C says soft iron ring, and then D says loop of copper wire. Now, the aim of keeping this material in any of these is to protect it from the influence of an external magnetic field. So whatever you are using to protect it must be something that will easily transfer the magnetic line of force away from that material. And of all these materials, the only one that easily allows magnetic field to permeate it is the soft iron ring. Now, if you recall, when we talked about soft iron ring, we said it is used in a particular process known as what? The magnetic shielding. Okay, so that is what is done in this process here. So you're actually shielding a material from external magnetic influences. So the correct option here is C. This is another question from the 2003 JAMB, and we have four statements here. The first one says, it retains its magnetism much longer than steel. Second one says, it is more easily magnetized than steel. The third one says, it is more easily demagnetized than steel. And then the fourth one says, it produces a stronger magnet than steel. Now, the question itself now says, which combination of the above makes iron preferable to steel in making electromagnets? Now, when we talk about electromagnets, we're talking about a magnetic substance placed in a solenoid, and then you allow current to flow such that it gains magnetism. Now, you want to make sure that that material is able to be magnetized fast and is able to lose its magnetism fast. Like, for example, one of the applications is when it is being used in a scrap yard to lift heavy scrap or separate metal from non-metals. Now, you want something that once you activate the circuit, will pick all the metals, and the moment you switch off the circuit, will drop them at the specified location. So you don't want something that retains magnetism over a long period, and at the same time, you don't want something that is too strong that will not be able to be demagnetized when you switch off the circuit. So that means the statement 1 and statement 4 do not make this particular electromagnets preferable. That is when you are using iron compared to steel. Now, since we want to look at what makes iron preferable, that means we are looking at the properties such as being easily magnetized and being easily demagnetized, which is what we see in statement 2 and statement 3. So that means the correct answer for this particular question would be the combination of statement 2, and statement 3. So whatever options carries 2 and 3 would be the correct one. And that's the answer to this problem. Here is another question, this time from the 2003 JAMB. And in the question we have 4 statements, so let's run through them one after the other. The first says, it retains its magnetism much longer than steel. The second says, it is more easily magnetized than steel. The third says, it is more easily demagnetized than steel. And then the fourth, it produces a stronger magnet than steel. Now the question itself says, which combination of the above make iron preferable to steel in making electromagnets? Okay, now when it comes to making electromagnets, you are passing current through a solenoid that has been embedded with a soft iron. Now, the reason why we are using soft iron core in this case is because you want a situation where that material will gain magnetism very fast and will easily lose the magnetism the moment you switch off the circuit, that is when no current is flowing through the solenoid. Like take for example, in the application where you're using an electromagnet in a scrapyard, you want to make sure that when you switch on the circuit, the electromagnet will be able to separate metals from non-metals or even pick up huge chunks of metal from a particular location to another point where once you switch off the circuit, it drops the metal at that location you want it to be. So you don't want it to be something that will linger, that when you switch off the circuit, the metal is still stuck to the electromagnet. You want to make sure that it drops immediately you switch off the circuit. So you want something that is easily magnetized and easily demagnetized. So the combination that makes iron preferable to steel in this situation will be what we see in statement 2 and statement 3. That means the answer to this question is 2 and 3 only. This question is taken from the West African Senior Secondary Certificate Examination. And it says, the force on a charge moving with a velocity v in a magnetic field B is half of the maximum force when the angle between V and B is. Now, when students see questions like this, they are always too quick to pick an answer. Okay, this is because one of the things that is mentioned in the class is we always talk about the maximum force and then the minimum force being at angle 90s and angle 0 degrees. Now, you recall when we did talk about force on a charge in a magnetic field. Remember, there are two equations that define this, and both of them go by F equals BVQ sine theta or F equals BIL sine theta. So you see that angle affects the force, right? But the key to answering this question lies here. He said it is half of the maximum force. So what you want to make sure of is that whatever you are multiplying by BIL or BVQ would give you half of what you should have gotten. So you want to make sure that sine theta will give you 0.5. So if sine theta is 0.5, that means theta itself will be what? Inverse sine of 0.5. And that will give you what? 30 degrees. Don't forget, if the question were to find the one that will give you maximum force is when theta is 90 degrees. Because sine 90 is 1 times BVQ remains BVQ, and same way 1 times BIL remains BIL. But when you're looking for the minimum force, that will be when theta is 0 degrees. Because sine 0 will give you 0. And multiply 0 by anything, you still get 0. That's the minimum possible force or the charge moving in a magnetic field. But in this case, we want it to be half of the maximum. So that is why we have to work around getting the angle that will give us 0.5. So that's why we say sine theta equals 0.5, which means theta itself is 30 degrees. Now you can practice with many other questions. Pick your questions from the WAEC past questions, JAMB past questions, or any other exams that you take, and try them out with all the principles that we've learned in this video. And if you do come across anyone that is challenging that you need some help with, you can always drop that question in the comment section of this video and we will attend to all of your questions. Now at this point, if you're still not subscribed to the channel, kindly take a moment, click the subscribe button. And one thing you can also do is to click the notification bell icon so that you don't miss our next video. And always share the video so that many other students like you can get access to the amazing content that we create right here on Oya Learn, your flawless school too. Please ensure that you share the video and encourage your friends to engage with the videos by liking the videos, dropping a comment, and also subscribing to the channel. I'll be seeing you in the next video. Bye for now.